Alright guys, so now we are going to talk a little bit about 3D vectors. So these are not simply your vectors in 2 dimensions, these are vectors in 3 dimensions. So if we're talking about component form, then instead of just having an x and a y, we're also going to have an x and a y and a z. If we're talking about unit vector form, then we're talking about an I, a j, and then we also introduce a k. Now these are called base vectors, and if we were to write these in component form, your I is really 1, 0, 0. Alright, so this corresponds to the x. The j would really be 0, 1, 0. That corresponds to the y. And your k is 0, 0, 1. Okay, so you're not going to be asked to, of course, draw this, or really rarely will you ever have to be able to visualize this, but understand that we have this dimension of depth which has been added onto it, and so we can express vectors in 3D. So what we talked about before is identical. The only difference is we are adding on another layer, so to speak. So maybe we're talking about vector AB, and let's say that it has components 2, -3, 4. Okay, again, the 2 is referring to the x component, the -3 is the y, and the 4 is the z component. Okay, so in unit vector form, we'd be talking about 2i minus 3j plus 4k. You're never going to be asked to express it in more than one form. They'll tell you if they want it in component form, which again we call column vector form, or maybe a question will ask you to express a vector in unit vector form. Remember the I, J, and the K, we call this unit vector form. And over here this is component form. Okay, but finding the magnitude. Okay, so we talked about how the absolute value symbol is really your symbol for the magnitude of that vector. Well, sometimes you actually will see the components written inside of that absolute value symbol. All right, or I suppose you could even have this 2i minus 3j plus 4k inside of that absolute value. Okay, remember this is referring to the magnitude or the length of this vector. Well, we said before in 2D it's really just Pythagorean theorem. Well, the good news is it's still going to be Pythagorean theorem, but just in 3D. So you're simply going to take your components and then you're going to square them just like we did in 2D, but we're just adding on one more dimension. Okay, so you would just go and simplify all of this. So we would get the square root of 29. That would be the length of this particular vector in 3D. And again, who cares what this actually looks like? That's really not important here. But we can still find the length of a vector in space, right, which is really what we call 3D, by doing Pythagorean theorem. Now, go to your formula sheet real quick, and you'll notice that there's not a lot of formulas given to you on the topic of vectors, but the first one given to you is the magnitude of a vector. So take a look at that. So this is how they present to you the formula for the magnitude of a vector. Again, this is given in your formula sheet. So you can see that here they're just using a lowercase letter. They're using lowercase v to represent the vector. We see the absolute value symbol around it, which again is our symbol for magnitude. And you can see that there are 3 different components here that are squared and then added together in our formula. Okay, so the v sub 1, v sub 2, v sub 3, that's just referring to the 3 different components. Okay, and let's just make sure that it's a little bit more clear that this v right here, which is identifying the vector, that one is bolded, whereas the other v's are just referring to the 3 different components. Okay. Okay, let's look at some more definitions. So here we're talking about what it means for 2 vectors to be equal. So 2 vectors are equal if they have the same direction and the same magnitude. So perhaps we're talking about a vector, which by the way, sometimes your textbook will show the direction of the vector by putting the arrow somewhere in the middle. understand that it has a start and an end. So maybe this is vector AB, and I'll draw another one, which, bear with me here, let's pretend that this is the same exact length, same exact direction. This one I'll put the arrow at the end, and let's call this one CD. So we can say that vector AB is equal to vector CD. All right. Again, let's suppose that we were told that AB has components. Now let's see, if we are going to the left and then down, the x component would need to be negative, so maybe that's -3, and the y component would also need to be negative. So let's suppose that is -5. Okay, so if we were to just improve our drawing here, maybe this is 3 and this is 5. Same thing over here. Okay, you would of course have graph paper to be certain that they are of the same dimensions. So we can see that the components are the same. Notice how these are both negative because we have to go to the left and we have to go down, right? So it's a negative x and a negative y direction. So that's showing that they have the same components, all right, which is really the same direction. Okay, so this is showing same direction. But if we were to show the same magnitude, we would of course have to do our Pythagorean theorem to get the magnitude. So that would simply be your 3 squared plus your 5 squared. So I know we're back to 2D here. So we'll constantly be going back and forth between 2D and 3D. All right, anytime we're looking to draw them, understandably so, we're going to be doing it in 2D. So this would be the square root of, what's that, 34. Okay? So we would say that they have the same magnitude and the same direction, so these vectors are equal. Okay? Sounds pretty obvious, right? And it really is. It's not that difficult. Okay, next let's talk about the negation of a vector. So the negation of a vector is where the vector is going to be reversing its direction, but the magnitude or the length is not going to be changing. So suppose we have vector AB and it has components 2, 5. Well, if we were to negate this vector AB, it's exactly what you would think. You would just negate the components. All right, so if we were to try to illustrate this, the vector with components 2, 5 would have an x component of 2, so we'd have to go, suppose you're starting here, we'd have to go to the right 2, and then we'd have to go up 5. All right, so this would be somewhat realistic, right, if we were going over 2 and then up 5, right? So notice how we have the arrow going in that direction. So if we were to negate it, if we were to draw this vector -2, -5, it would start at a point, let's say right there, and then it would go in the opposite direction. All right, and so you can see here, if we were to kind of reverse it, that's 2 and that's 5. Okay, the size would still remain the same, but it's just the direction that is getting negated. So in general, we can say that the negation of vector AB is actually going to become BA. So if we're keeping the length the same but just reversing the direction, then you're really just reversing the order of your letters. So let me go back here and label this A and label this guy B. All right, and so now this is still B and this is still A, but you can see that the negation of vector AB is really just vector BA. And we can take this a step further. We could say that vector AB is the same as the negation of vector BA. So think of it as you're just dividing that negative over to the other side. Okay? So what this is really suggesting is that if you want to reverse the order of your letters, just simply negate the vector. So we'll just jot that down. To reverse the order of the points in your vector, you're going to simply just negate the vector. Okay, and finally let's talk about parallel vectors. So we say that two vectors are parallel if one is a scalar multiple of the other. So remember we talked about how a scalar is just a fixed number, it's a quantity, it doesn't have direction, okay? So it's just some number, okay? And we're going to be multiplying a vector by some number. So that's the idea behind a scalar multiple. So what the heck am I talking about? Well, suppose we have vector v has components 2, 3. And suppose we wish to multiply this vector v by, how about 4? So if we were to do 4 times v, all right, now this 4, we call this the scalar, all right? And so common sense would tell you that we would just multiply these components by 4, so that would give us 8 and 12, okay? So these two vectors here are parallel, all right, and the reason we know they're parallel, if we were to just kind of graph this, vector 2, 3 would look maybe something like this, okay, over 2, up 3, so here's my vector v, all right. So again, just to draw in the components here so you can see it's over 2, up 3, let's say. If we were to draw in vector 4v, so you can place it anywhere, it doesn't matter where you put it. If we were to draw in these components, all right, draw in this vector, this is over 8 and then up 12. Okay, sorry it's not very drawn to scale, but hopefully you get the idea. So this is the vector 4v. You can see that, well, had I drawn this with graph paper, these are parallel to one another. Okay. Now, keep in mind that we could also negate the vector. Suppose we were to look at negative 3v. Negative 3v would have components, I'm going back to v, and I'm going to multiply it by the scalar of negative 3. So that would give me negative 6 and then negative 9. If I were to draw this vector, so let's maybe start it here, we would have to go down this way. All right, so the components here, well, I'll just label this as a positive 6 and a positive 9, but because we're going to the left and we're going down, we know the components would be negative 6 and negative 9, okay? But notice how, again, if we were to draw it accurately, you'd be able to see that this is also parallel. Even though the direction has been reversed, they are still parallel, all right, to the other ones that are going in the opposite direction, okay? So vectors can be heading in different directions and still be parallel. The key is that they need to be scalar multiples. All right, a scalar can be negative. Maybe jot that down, okay? So it's the idea that, you know, the scalar in this case is 4. The scalar down here is that negative 3, okay? So as long as they're multiples, we can say that they're parallel. Okay, so last example, if you can handle this one, then you have a really good understanding of parallel vectors and you are in good shape. So we're looking to find t, and we're told that v is parallel to w. So there's your parallel symbol. And t shows up right here as the y component of vector v. Notice we have all the other numbers there for the other components. So look at the relationship here. If we were to compare the x components, compare the z components, notice that to get our vector v, we would have to take vector w and multiply it by 4. So if we look at it that way, this scalar would be 4. If you reversed it, vector w, this is found by doing a quarter of v. All right, if you take a quarter of those numbers, if you divide those numbers by 4, you will get the numbers of w. So working backwards here, notice how this is a 6, all right? And so if we are going to work backwards here, you would, to find t, you would simply have to do that 6 times 4. Again, you're just using kind of common sense. Look at the pattern, right? So t would have to be 24, all right, for this scalar relationship to remain intact, all right? So you can say the scalar is either 4 if you go in that direction or a quarter, depending on which way you want to go. Okay, time for lunch. Bye-bye.